Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In algebraic geometry, the canonical sheaf and also the canonical divisor are extremely important invariants to study algebraic varieties. But this begs the question, how do you actually calculate this canonical divisor? In this video, I want to tell you a very important method for doing so, and it's called the Riemann Hurwitz formula. And there are two ingredients that are involved in this Riemann Hurwitz formula. We need to know about degrees of finite maps and ramification. So let's have a look at the notion of a degree of a finite map. Now in this video today, I want to use a fair bit of manifold theory. So I want to assume that we work over the complex numbers, but actually much of this theory goes over more generally to an arbitrary algebraically closed field. One point of subtlety is that once you're in positive characteristic, you can get into a situation where you have inseparable field extensions. Okay, so that's another subtle point. Okay, so let's start with the notion of a degree. Okay, so what's that looking at? So suppose now we have two projective curves, x and y. Okay, we have a regular map between them, phi from x to y. That's a non-constant map of projective curves. We're going to define the degree of phi, so this is going to be a it's going to be a positive integer, and it's denoted dig phi, and it's given by any of these three equivalent definitions here. Okay, so the easiest way to define it, okay, directly is as follows. Okay, so you can pull back functions from y to x. Okay, so in particular you can pull back rational functions. So that means that this k of x, the function field of x, is a field extension of the function field of y, and you can ask what is the degree of this extension. So this will be some positive integer, this d here. Another thing is that you can look at the map geometrically. So suppose your map of curves is like this one here, and what do we see here? Well, in this case here, it's generically 3 to 1. Okay, so what do I mean by that? So suppose I pick a point down on the bottom here. Maybe that's called y. So above it, what do we see? We see that there are 3 points. So it maps 3 points to 1. And if we shift this point over, it usually maps 3 to 1. But sometimes two of the points might come together, and it won't be a 3 to 1 there. But generically, it'll be 3 to 1 in this picture. And generically, this map phi, since it's non-constant, it's not going to be infinity to 1. It's going to be finite to 1. And the generic number that it is, finite to 1, that's the d. That gives you the degree. And finally, another way to define this is you look at any divisor down here on y. We can talk about its degree. Okay, so the degree of this d. And we can also pull back the divisor. And when you pull that divisor, that gives you phi upper star of d. And what's the degree of that? That's related to the original degree of d, by multiplying by this number d, which is the degree of phi. So the degree of phi upper star d is the degree of phi times the degree of d. Let me kind of give you just a pictorial explanation for why this is true. So this is how you should be thinking about these sorts of notions, okay? Which is better than thinking going through the proof right now. So remember, this k of x is a field extension of k of y, and since we have a separable field extension in this case, there's a primitive element theta. Okay, so let's take that primitive element, and you can look at the minimal polynomial of this theta over k of y. Okay, so it'll be some minimal polynomial like this, t to the d, a polynomial in say t, plus fd minus 1, t to the d minus 1, all the way down to f0. The coefficients here are in the small field k of y, just rational functions on y. And what you'll note is, what is this d here? This d here is going to be the degree of this extension. Okay, so that's the first thing. You have a minimal polynomial, and if we're assuming part 1, okay, then this d is just this the degree of this extension. Okay, so what can you do? So now suppose you pick a point inside this k of y, so this y. Okay, so firstly these f's, okay, they're rational functions, so they're not defined on all of y, but let's look at the place where all of those coefficients are defined. Okay, so that's some sort of open set inside here. Okay, and then for those points you can specialize those coefficients to any particular point, like this one here. Okay, so you can specialize. Suppose it's defined on something like this. Okay, that open set. You can specialize to any particular point. And when you specialize to that particular point, all of these f's will give you actual complex numbers. Okay? And then basically what this is saying is that what is x above here is just the solutions, the zeros, of this complex polynomial. And of course there'll be exactly d of them. Okay? If you include multiplicity. And the point is that generically there will actually be d of them. Okay? So generically there'll be d separate solutions. Okay? And only in special cases will these actually collide, like you see here. Okay? So that's the reason why you get the same number here. Generically it's d to 1. And finally, what happens with this divisor here? Well, to prove this statement, I guess, since both sides are kind of linear in this divisor d, linear as a function of d, we just have to do it for the generators, okay, and that means for a single point. And if you pick a point like this y here, okay, that has degree 1, and you look at its inverse image, the pullback will be just the sum of these d points here. So on the left-hand side you'll get d, and on the right-hand side you'll have d times 1. And so that's why the third way of looking at this degree of phi is the same as the other two. Okay, so that's the notion of a degree of a finite map. Okay, so I guess really the first two you can define more generally. The third one you do know projectivity. Okay, so now let's move on to the notion of ramification. And one way to think about ramification is to think about, well, if you have a map of smooth curves, okay, when is it a local diffeomorphism? And if it's not a local diffeomorphism, how much does it differ from a local diffeomorphism? Okay, so let's look now at the situation where the x and y now are smooth curves. Not necessarily projective here, but let's suppose they're smooth curves. And now we have phi is some non-constant map. Okay, we want to be in the situation of non-constant map, so we have a finite map here. Well, yeah, usually we'll have a finite map if it's also projective at least. And then we can just pick a point on this x here upstairs. Maybe this top one here, let's call it x. And let's work with charts, okay? So we've got a complex manifold in the smooth case. So maybe we have a u subscript x here, that's a chart, okay? And we'll also look at its image downstairs, y, and we'll look at your chart there, say u, y. And when I mean chart, that means that I'm going to take this open set and there's going to be some biholomorphic map to some open subset of the complex number. So C maybe with the variable z. And we can assume that the x corresponds to the 0 here, okay, just by translating if necessary. And similarly, we'll have another chart for this uy. Okay, so we'll identify this with some open neighborhood of 0, so y corresponds to 0 here. Okay, great. So let's see now what happens in this proposition definition 2. What types of things are happening locally with this map here? Okay, so well, firstly, in charts, you're just going from complex numbers, open neighborhood of 0 to open neighborhood of 0. So this is the z coordinate. This is given by a w coordinate. Okay, so this w is some function of the z's. W is some function of the z's. And since we're assuming that the 0, the x maps to y, so the 0 goes to 0 here. When you look on the charts, there's no constant term. Okay, z equals 0 corresponds to w equals 0. So w, of course, it's holomorphic, so it's given by some power series in z. And the constant term of 0, because we're assuming 0 gets mapped to 0. So it's a power series, and the 0th term is 0. So let's look at the first non-zero term, and let's suppose that's the z to the e term. So we assume here that the coefficient of z to the ae is non-zero, but all the earlier coefficients are 0. And otherwise you have some sort of power series. Okay, and let's see what's happening locally there. Okay, so locally there, what happens is in a neighborhood of x, phi is e to 1 except at x. Okay, so in this case here, locally at x, it's 1 to 1. But let's pick another situation. If you picked your x over here, okay, and this gets mapped down to this point here, what happens is that at this point it's 1 to 1, but in a neighborhood outside, any small neighborhood around this, it's going to be 2 to 1 there, okay? So in general, the claim is that it's going to be e to 1, except at that point. At that point, it will be 1 to 1, okay? But if you move slightly away from it, it will be e to 1. And that e is given by this index up here. Okay. Also, in a neighborhood of this point x, what can you say? So we want to work in the canonical sheaf, right? So the canonical sheaf is generated by these differentials. So downstairs, you'll have a dw, and you can pull that differential back upstairs. So you can take a dw, and you pull it back up phi upper star of dw, and that'll be some differential up on x. So you have some differential up on x here, okay? So you'll have something down here, a dw, and you're going to pull it up to a phi upper star dw, up there. And that's going to be inside this omega x, and you can say, well, this dw, it generates the cotangent bundle downstairs. It's going to span this at every, spans the cotangent space wherever it's defined, okay? But this might not. Okay, so let's see what that is. Well, it says here that this has, this is inside here. It's going to be a section of this, okay? It's going to be a non-zero section, but it has an isolated zero at x of order e minus 1, okay? So if e equals 1, there's basically no zero, so it's going to give you an isomorphism, okay? So that's going to be the, so in that case here, this will span the cotangent space here when e equals 1, okay? But if e is bigger than 1, then it spans the cotangent space in a neighborhood of x except at x itself, where it has a 0 of order e minus 1. Okay, so maybe we'll talk a little bit more on the next board. But let's just look at part 3, which says that, well, when is phi a local diffeomorphism? It's a local diffeomorphism precisely when e equals 1. Okay, so when e equals 1, it's like this situation here. It's 1 to 1 everywhere in a neighborhood of this x. Okay, of course, if it's e to 1 in a neighborhood except at that point, then it can't possibly be a local diffeomorphism. Okay, because a local diffeomorphism is 1 to 1 everywhere in a neighborhood. Okay. So that's the situation. This number e detects when something is a local diffeomorphism, okay? And in that case there, we say that this phi is unramified at x. Okay, that's the situation. Phi is unramified at x, okay? So that's good. This number e is some way to say when something is a local diffeomorphism. But it's not just a binary thing, either is a local diffeomorphism, it's not. It actually is a number, so you can actually say how far you are away from being a local diffeomorphism. So in that case, when e doesn't equal 1, we say that phi ramifies at x, so it's not a local diffeomorphism. And this number e is a measure of how far it fails to be a local diffeomorphism, and we call it the ramification index. E is the ramification index. And where the place where it is not a local diffeomorphism, we call it a ramification point. Okay, so there's some very important definitions here that occur in the study of algebraic geometry. Okay, so perhaps the most simple part is part 2, which is just a calculation, which hopefully shows you what's going on. Okay, so suppose you look at phi upper star of dw. Okay, we're looking at this. This is a differential up on x, okay, and we'll just work on it using the charts, okay. So this is a differential, so in the neighborhood of this x, this has to be some sort of multiple of dz, and it's going to be some regular function times z, and let's see what it is. Well, you just differentiate this, so dw, okay, when you differentiate that, is just, you differentiate this term to get e times ae, z to the e minus 1, plus, and you just keep going, okay, you differentiate term by term. And what you'll see here is that, of course, this does not generate all of the cotangent bundle, okay, that sheaf or the corresponding sheaf that's generated by this dz, because you have this term here, which has a 0 of order e minus 1. So if e equals 1, of course, that's just a constant, so you'll generate all, you can have anything times dz when you multiply this. But in this case here, you'll have a 0 of order e minus 1 when e is greater than 1. Okay, so let's look at part 1 now. So why is this true? And we do that by taking doing a change of variable. So we look at this right-hand side, and one of the things that you can do, since this is a power series, is that you can actually take the eth root of that. Okay, and that will also be a power series. Okay, so how do you do that? Well, firstly, you pull out the z to the e, and you take the z eth root of that. Okay, so you take the eth root of z to the e, so that's just z. Okay, and then once you pull out a z to the e, you have a power series with a non-zero constant term, and any power series with a non-zero constant term, you can take the eth root of that. So at the end of the day, you'll get a new power series which has the form some eth root of ae, that first coefficient, times z, plus and then higher order terms, and this will be an actual power series. And I'm just going to change variables with this u. Okay, and since this is a starts in degree 1, you can see that this is biholomorphic. Okay, so you can actually invert that. This is the case where you have a local diffeomorphism. Okay, so yeah, so another way to see this part 1 here. Okay, so why is the case that e equals 1 corresponds to a local diffeomorphism? Okay, so this is essentially the inverse function theorem. Okay, so you want to look at the derivative and see when that is 0 at 0. Okay, so if you look at the case where e is at least 2, when you look at the derivative of this, you will have some power of z that's not the 0th power, so that means that 0 will be 0. Okay, so the inverse function theorem will tell you that that's not a local diffeomorphism, but when e equals 1, when you differentiate it, you'll just get this constant term which is non-zero. Okay, so the inverse function theorem tells you that it is biholomorphic. Okay, so in this case here, this change of variables, it's biholomorphic, and so we can take this eth root and change variables. And if you change variables, of course, what happens is that w equals, well, this is now, the eth root of this was this new u, so w equals u to the e, w equals u to the e. And if you think about this term w equals u to the e, okay, it's quite easy to see that, well, when u equals 0, okay, so when does w equal 0? Just when u equals 0. But if you make it w any slightly bigger complex number, there will be e distinct roots of that w, okay, because they'll differ by the e distinct roots of unity. And here again, we're going to use the fact that we're working over the complex numbers, so that eth roots of unity are all distinct. As I said, if you work in positive characteristics, there are some subtleties that can go on, and this theory of ramification has to be modified a little bit to incorporate such subtleties. Okay, great. So this essentially completes the explanation for why this proposition definition holds, and it gives us a way of talking about when of relating the cotangent bundle in a map like this. Okay, so what's the upshot of what's going on here? So this is kind of the key point, which is going to allow us to look at the Riemann Hurwitz formula. Okay, so the point is the following. Okay, so we've got a map of curves here, and the key question here is, well, can you relate the canonical sheaves and the canonical divisors on these two curves? That's the question. So the first thing is that we do have a relationship between the canonical sheaves, and that's quite easy. Okay, you look at omega y. Okay, there's going to be the sheaf of differentials here. Okay, and you can pull back a sheaf of any differential here upstairs. Okay, so that means that you have a morphism of sheaves from phi upper star of omega y. You pull this back up to here into omega x. So this is a homomorphism. So it's a homomorphism. It's the section S inside homomorphisms from phi upper star omega y to omega x. And remember, omega y and omega x, these are invertible sheaves. Okay, so the usual trick we can do, the same is true of phi upper star omega y, so this is still an invertible sheaf, and so we can use the Morita equivalence. Okay, so the equivalence of categories and tensor by the inverse of this invertible sheaf to say that this is homomorphism O into omega x, tensor the inverse of this, which is also phi upper star the inverse of omega y, or omega y star, the dual. okay? And Homs from O into something like that is just a global section. So this is a global section of this invertible sheaf here, omega x tensor, the inverse of phi upper star omega y, or phi upper star of the inverse of omega y. Okay, they're the same thing. And remember, the inverse is just given by the dual. Okay. So, so basically, what this is going to do is we can think of this as kind of like this divided by that. So this is like the difference between these two. Right? So you want to compare omega x and omega y, and this is sort of measuring the difference between the two. And what is the difference between these two? So the way you think of this is, well, this is a section of an invertible sheaf, so it corresponds to an effective divisor, and that effective divisor is called the ramification divisor. We'll denote it here with R, this ramification divisor, and it's a divisor up on here, we're working up on x at the top here. Okay, so that's my R here. Okay, how does this correspondence work? Well, one of the most important things is that this O of R is such that if you look at all the functions, okay, which have pole at most given by R, okay, this sheaf here of rational functions with pole at most given by what's in R, then it's actually isomorphic to this omega x tensor phi upper star omega y star, that invertible sheaf. And the thing is that, well, what is this equal to? Actually, this proposition definition tells you, especially part 2, what that is. Okay. So the point is that where it's a local diffeomorphism, okay, if you have this dw here, you pull it back up. In a neighborhood here, you'll have a local diffeomorphism, so you'll get the same cotangent bundle here as up as the pullback of this up here is the same as the cotangent bundle on this x. Okay, so you're going to get the same thing. So the only place where it's not going to be the same is where it's not a local diffeomorphism. That's at a ramification point, and that's here. And the question is, well, how much does it differ there? Okay, that's where the ramification tells you. So this R is supported at ramification points, and in fact, you can say more about it. Okay, so for example, here, if you pull back the differential, which generates here, this dw up to here, okay, what happens is the ramification index here, it's generically 2 to 1. And this part 2 tells you that there's a 0 of order 2 minus 1, so that's 1 here. So that will tell you that this R is supported at this point with multiplicity 1 here, for example. Okay. So this gives you complete information about R. You can just read it off from this part 2 here. Okay. And now we're ready to give the Riemann Hurwitz formula. Let's now state the Riemann Hurwitz formula. Okay. So suppose now we have a smooth projective curves x and y and a non-constant regular morphism phi from x to y. We'll work here over the complex numbers. So since this is a finite map of these smooth projective curves, we can talk about ramification points. So suppose the ramification points, and they'll be finite in number, p1 up to pm, and associated to those ramification points will be these integers, at least 2. The ramification indices, and let's suppose they're e1 up to em. Remember what we said is that the ramification divisor, we'll denote that with R, is supported at these points. It's going to be a linear combination of these pi's, and the multiplicity at pi is just given by that 0 we computed for that differential we pulled back. So this is just going to be the ramification index ei minus 1. Okay. And what does the Riemann Hurwitz formula do? It relates the degree of the canonical divisor on x upstairs to the degree of the canonical divisor on y downstairs. Okay, and the formula is as follows. This difference, okay, not the exact difference, but degree of kx minus the degree of phi times the degree of ky is just equal to the degree of this ramification divisor. And the degree of this ramification divisor is quite easy to compute here using these ramification indices, and we'll see an example of this later. It's just the sum of these coefficients over here. So let me show you why this is true, and it's now quite easy. We've got all the elements that we need, and we just need to prove this first equality here. Okay, so the degree of this R is of course just the degree of this O of R, and O of R, remember, we defined it as just this quotient of invertible sheaves, so to speak. So it's the omega x tensor, the inverse of phi upper star omega y star. So we don't need that second word degree there. Okay, so this is just this sheaf here, omega x tensor phi upper star omega y star. Okay. Now the degree is a group homomorphism. Okay, so it takes this tensor product to a sum. So this is the degree of omega x plus the degree of this thing here. And by that first proposition definition I gave you about the definition of the degree of phi, this is just the degree of phi times the degree of this omega y star. Okay. Now, of course, the degree of omega x is just the same as the degree of kx. The degree of omega y is the same as the degree of ky. And also the fact that degree is a homomorphism means that the degree of omega y star is just negative the degree of ky. And finally, this gives us the formula that we want. This is the left-hand side, what we see in the Riemann Hurwitz formula. And this gives us the right-hand side over here. Okay, so that's the wonderful formula. And it's actually quite useful. And this is the one that we use fairly often to compute these canonical divisors. Okay, so let's see a simple example, one which will be very useful for us. Okay, suppose now we look at plane curves. Can this tell us about the canonical divisor and hence the genus of a plane curve? And the answer is yes. Okay, suppose x is a plane curve, so it embeds inside P2. And if it's a plane curve inside P2, we'll assume it's smooth, and it has a degree, so it's given by the zeros of some homogeneous degree D polynomial, so it's degree D. In this case, then this degree of this kx, this canonical divisor, is a simple function of D. It's just D times D minus 3. Okay, and maybe the time you want to have a look at it, so let's just look at some simple instances of this. Okay, so some simple instances that you'll see is when D equals 3, that's the easiest one probably. This will be 0, and that corresponds, of course, when this is 0. Okay, and that's because actually in this case the kx will be 0. Okay, so it's going to be the case of an elliptical cubic curve. Okay, so it's so it has genus 1. That's the genus 1 case, and you can check for both 1 and 2. So if D equals 1, you get 1 times minus 1 minus 2 is minus 2, so that's minus 2, and minus 2, that's the degree of k of the projective line. So of course if it's a degree 1 case, you've got a line. A degree 2 case, you have a conic. So when you have 2 here, it's 2 times 2 minus 3, so that's minus 2, and we know that the conic is also isomorphic to the projective line. Okay, so the low degree cases, we've seen examples of all of them. Okay, so let's see how to prove this, and it's quite nice, and hopefully this will also reinforce some of the ideas that we've talked about in this video. Okay, so we need a map. Okay, and the way we'll do it is we have this x here, there's my degree D curve inside here, and we're going to compare it to P1. So we need a map to P1, and the way we'll do that is we'll pick some point Q, which is not on x, and we'll just project away from it. So what does project away from it mean? Okay, so I guess you can do it in various ways. One way to do it is you can actually draw a second curve, a line that's away from Q. And any point here, you just draw a line from Q to this point, and it just maps to this point on the line. Or you can think of this P1 as just the set of lines to this point. So everything that's on this particular line here, okay, all these 3 points will get to that, sent to that particular line, which represents a point on P1. Okay, or you can just project it onto this point here on the purple line. It's up to how you want to think about that. Okay, so certainly we can do that. Now we can do some change of coordinates, which is going to change the isomorphism class of this x. So in particular, we can change it so that Q is at 0, 0, 1. And then we can just rearrange things so that when we do the projection, okay, let's just work in the affine patch so it's a little bit easier just to do the calculation. And you can see what's going on there. So the affine patch with coordinates x, y, then this x is given by a degree D polynomial in x and y. Suppose that's called f. And you can arrange it so that the projection is just given by, well, what's happening to the x and y coordinate. You just project onto the x coordinate. So that's another reason why it's called a projection. So that's a fairly elementary calculation that you can do so that you can do that. And then the next thing that we need to do to be able to use this formula, okay, what do we need to do? So I guess we need a couple of things. We need the degree of this phi. So what's the degree of it? Well, it's going to be, you're projecting, say, onto this line here. So everything that's on any orange line, okay, they're the things which get sent to the same point down here. So how many points does a line intersect a degree D curve? D times. So this degree of phi phi is generically d to 1. Okay, so the degree is equal to d. So that's the first thing we can compute. The other thing we need to compute are the ramification points and the ramification divisors. So that's going to be where, when you move this curve around, you'll see a tangent. So now we've changed so that we're looking, basically we're projecting vertically. Okay, so we're just projecting vertically. And then when we're projecting vertically, so for each x, okay, we might as well fix that x, and we want to say, is there ramification points above there? So are there tangent lines? So for there to be tangent lines, that means that df dy is equal to 0. Okay, that's the usual condition, remember, to say that there's a double root. Okay, the double root, that's where you have the tangent c. Okay, so at least in this a to xy, the ramification points are given by, well, firstly you have to be on the curve f equals 0. And then once you're on that curve, okay, you want to check this condition df dy is equal to 0 for the tangent c. And this suggests to you, so this is the part where it's not complete, but it gives you the proper calculation, and you can make this a proper argument, is that, well, what you do now is looking back over in the projective case, you've got the curve that completes this f equals 0, so basically it's completion of that, so that's the original curve x. And you intersect it by what happens when you look at df dy, okay? And what's the degree of this? The degree of this is d minus 1. So you intersect it with this degree d minus 1 curve. And Bezout's theorem tells you that when you intersect x, that degree d curve, with this curve which gives you the condition to be tangent, which is degree d minus 1, the number of intersection points is, if you include multiplicity, d times d minus 1. And actually this will give you the correct formula for what is the degree of the ramification divisor, okay? And this includes the case where some of those points may collide, so the point of tangency, okay, so the point of tangency could be multiple, so the ramification index might be even bigger than 2, okay? And now we can just put everything into the Riemann Hurwitz formula. So what's the degree of this kx? We shift this to the other side, so that's the degree of phi times the degree of, we're mapping to p1, so the degree of kp1. And then you add in the degree of this ramification index, which we just computed to be d times d minus 1. Let's compute this first term here, the degree of phi, as I said, it's d to 1, okay? And then the degree of kp1, remember this, the canonical sheaf is O minus 2, so the degree of that is minus 2. So it's minus 2d plus this d times this d minus 1. So pulling out the common d here, okay, you'll have d times, and you've got minus 2 plus d minus 1, that gives you d times d minus 3. So this is a rather beautiful and well-known formula for the degree of canonical divisor of a plane curve. Okay, it's a simple function of d, and this allows you to compute also the genus of a degree d curve on the of a plane curve, smooth plane curve. I hope you enjoyed this adventure in pure mathematics.